So in this lecture, I wanted to go over acceleration, but I'm going to start here with a kind of mini lecture over instantaneous velocity. Instantaneous velocity is the average velocity over a tiny time interval. So when the time difference becomes very small, you're taking instantaneous velocity. And when the time difference becomes very large, you're taking average velocity. Because if you remember back to your formula on velocity, it's change in position over time. But this is really a delta down here too. And you can expand it out into a final position minus an initial position over a final time minus an initial time. So when that difference in time, TF minus TI, is large, it's average velocity, and when it's small, it's instantaneous. So how small is small enough? Well, the smaller the better, as it turns out. How can you determine instantaneous velocity? So in this class, to find instantaneous velocity, what we're going to do is we're going to take the slope of a tangent line. Yeah, and the other way is to calculate. So that would be graphically the first one. The second way would be to calculate V when delta t is small. Hopefully you can see that. I don't know how tough those are to make out. Let's do a little highlighting. Okay, so there you go. Two ways right there. When is it useful to find instantaneous velocity? So when I was talking about the slope of a tangent line to the curve, I meant when the line is curved. So instantaneous velocity can be useful if the line is doing a lot of different things at different times. So I'm just going to write when the line is curved. Whoops. Using bullets, so change it to a bullet point. All right, so when the line is curved. Okay, so we have some graph paper here, and actually I think I'm just going to add a page instead. See if I remember how to do that. Okay, and then we'll just add it down here. Add another one. What the heck, we'll add 3 just to be on the safe side. All right, so I want to make a graph now of a curved line to show you what a tangent line is, because some of you probably know from math class, you're like, oh yeah, I understand tangent lines, and some of you are probably like, no, I don't know. What am I doing? Okay. All right, so let's go right here to this first graph, and let's go ahead and make a graph. Let's just draw our axis. You obviously can use the graph paper that's already on the note guide, except it's just kind of small. All right, so when we make these position versus time curves, we always put the position on the y-axis. Notice that x is on the y-axis. X means position, right? So this is position over here. And time goes on the x-axis, always. And then 0, or the origin, is right there where the two axes meet. What else did I want to say? I guess that's about it. So let's go ahead and draw this curve. We're going to draw a parabola, or half of a parabola. And it's going to look like that. It's a curved line. So obviously taking the slope of the line at different points is going to be different. For instance, the slope of the line, maybe at this time right here, let's see if I can pick a time right here, is going to be different than the slope of the line at this time right here. And maybe I'll call this, I don't know, I'm just going to give it a name. I'm going to call it T1, and I'll call this one T2. And so why is the slope different? Because the slope is going to look like this right here, right? It's a tangent line. Tangent line is a straight line that only touches the curve at one point. And you might say, well, it looks like it touched at a bunch of points. Yeah, because I can't draw. All right, so so right here, though, is the only point it should have touched the line at. All right, so that was just a pretty crummy drawing. I can erase it and try it again if you want to see some better effort from me. Let's try it one more time. Oh, dang it. Oh, yeah. Saved by technology right there. All right, same thing. Let's do it one more time. Right there, right? Maybe we should get a different color because this is a different slope. And that's kind of my main point. Oh, dang. Not great. Not great at all. I thought I could grab that. Let me try that one more time. I think you get the idea. That red line was so perfect. Why can't they all be like that? Okay. All right, that's about as good as I'm going to get. But the idea is like the red line. The red line is so perfect. I mean, it looks like it might hit multiple times. It hits that black curve, but you get the idea, right? It's only supposed to touch it at one curve or one point, and that's it. And furthermore, you see that these are instantaneous velocities. These slopes are different based on these two times. So if you want to know the velocity of the object, whatever it is, at time 1, you just take any 2 points on this red line, which is the tangent line, any 2 points. I can draw an infinite number of points here and calculate the slope, and that's the velocity at that time at t1. And then on the purple line, if you want to know the slope on the purple line, you just find 2 points on the purple line right there and there and calculate the slope there. Could I have used the one in the middle? Sure. You could have used the position at time 2. And I hope you're comfortable with me saying that, right? Because the position at time 2, let me get a different color. Here's time 2. If I just follow it up to the black curve and then I move over, right, that right here, this x value is the position at time 2. The position at time 1, right, hopefully this makes sense and you remember this, is right here, and that's x1. So anyways, and that's at time 1. I think you kind of get the idea. So slope of the tangent line is the instantaneous velocity. And this kind of gets at the idea that you can't just use average velocity all the time in this class, right? Because think about it, right? If I draw that curve again, or try to, I don't know if I can make such a perfect curve twice. We'll see. All right. Yeah, not quite feeling that one as much, but that's all right. What we're going to do, if we did just the average velocity, and this object started at time, trying to make it a little bit better, started at time 0 right there. So then we would know that this is t0, or initial time, right? And that's value is 0. And then maybe t2 is the final position of this curve, which maybe that's right here. Looks like it goes past that, right? So maybe I just erase. Uh-oh, not all my curve. Oh, why you hate me? Oh, God. All right, let's try this again. Not giving up. All right. And T2 or TF, we'll put time final right there. So now you do the slope of this line, right? And you just take this line. We're gonna use purple. Let's use blue, navy blue. And that is the average velocity. So whereas if these curves are the same, right, let's pretend that both graphs are the same, this slope right here equals V average, whereas the red line has the slope, that would be the instantaneous velocity for time 1. I'll call that V1, right? And the slope of this purple line is equal to the instantaneous velocity at time 2. And so now you can see the difference and the need for instantaneous velocity, the red slope and the purple slope, versus an average velocity, the blue slope, right? Now, and the math is the same, right? You just pull your points from different places. For the instantaneous, you pull them off the tangent line, which is the red line and the purple line, based on what time you're working with. And for the average, you pull it off of just the black line, actually, and you pull the final and initial points off that black line. And I tried to pick the very final of final points, right, for TF. And I tried to pick the very initial, the most initial of initial, right, the time 0 for TI. And that kind of gets at the need for both and how you can graphically calculate both and why there is both. All right, I'm going to pause it there for a second, and then I'm going to add on to that. But what I'm going to add on is a more complicated reasoning for it, and you can see if you can follow. All right, so after we talked about what instantaneous velocity is, I want to now talk about average acceleration. So just like we called it average velocity, acceleration average, already. Let me just erase that and rewrite that. Acceleration average, or A average, is equal to the change in velocity over the change in time, right? And just like before, how with velocity we didn't have to write the average sign, we can just write A. And just like before with velocity, we didn't have to write the delta on the t, we can write our formula just like this. That acceleration is equal to the change in velocity over time. What's probably one more useful way to write that? We probably should write that before I move on to number 5. That would be this way, that A is equal to VF minus VI over TF minus TI. So, okay, I guess that's all right. So there is a delta on bottom. We just don't always write it. Is kind of the idea. And so we can split that VF and VI, or that delta V into VF and VI. We can split that delta T into TF and TI. Okay, so write the formula of average acceleration in words. I would say that acceleration is how quickly, maybe how slowly or quickly. Quickly? Does that sound right? It doesn't sound right. How slowly or fast? That sounds a little bit better. I'm not an English teacher. Slowly or fast? Sounds a little bit better. It still sounds awkward. How slowly or fast that the velocity changes. So it's the rate of change of velocity. That's another way to write it. I'll write it right here. Okay. Making sense of the units for acceleration. Okay, so what we see here, if we have velocity over time, right, or change in velocity over time, that our units here are going to equal meters per second for velocity, right, or that change in velocity, and then seconds for time. All right, well, that's kind of crazy looking, right? How do we deal with that? Well, what we have to realize is when we see meters per second on bottom, that's really, or let's think of it this way. Meters per second divided by seconds is the same as taking meters per second and multiplying by 1/seconds. This is like me saying if I take 4/2, which we all know is equal to 2, that's like me saying 4/2 is the same as 4 times, right, 4/1 times 1/2. And we would agree with that, right? So I can do the same logic here and say meters per second times 1/seconds, because we're taking meters per second and dividing by seconds. That's the same as multiplying by 1/seconds, is going to give me then, well, on the top, it'll just be meters. I don't know why my M looks like that. And on the bottom, it would be seconds squared. And so the key idea here is this, that the units for acceleration are, let me get a different color highlighter, are meters per second per second. All right, that's how we like to say that. So I can write that down right here, that you can pronounce that as meters per second per second. Right? Because what we're doing there is we're saying how quickly or slowly our velocity changes. Maybe it changes by 1 meter per second every second, right? Or it decreases by 1 meter per second every second. Something along those lines. Okay. So we're left with, even though that's the way we like to say it, right, is meters per second, mathematically, that is the same. Whoa, what just happened? That's not cool. Mathematically, that's the same as saying meters per second squared. And so a lot of times we'll just write meters per second squared, even though that is the same deal as meters per second. Okay. Like displacement and velocity, acceleration has both a magnitude and a direction. And so, because that's true, that it has both magnitude and direction, that means acceleration is a vector. So you can write that acceleration with the little vector hat over it, right, is equal to the change in velocity, which is also a vector, divided by time. So acceleration is going to have a sign, right? Whether it's positive or negative acceleration, that's going to indicate accelerating to the right or to the left. And then that gets tricky really fast, because what we'll see is that negative acceleration is the same. So negative acceleration is the same as deceleration, in that accelerating to the left is the same as decelerating to the right. So when you're slowing down, you're changing your velocity to the right and you're slowing down, that's the same as accelerating to the left. And that's kind of tricky to think about. We'll come back to that as we get further into this. But yeah. Okay, so if we make a graph of velocity versus time, and we have an axis here, I think I can use this one. I'm not going to be that picky here. So we're going to make a velocity versus time graph, and we'll put velocity on the y-axis, and we'll put time on the x-axis, because that's where time always goes, right? And then we'll label these points. The first one is 4, 4. So looks like 4 is right here. Oh boy, there's a little bit of a eye test here. Okay, so there's 4, 4. When the time is 8 seconds, the velocity is 8. So maybe about right there. Oh boy, struggling. Let's see if I can get that a little bit better. All right, and then when the time is 12, the velocity is also 12. It should be an easy graph to make, but with all this, these tiny squares, it's kind of tough on my eyes. All right, let's get a color here. I don't know. Let's go with brown. We never use brown. All right. So another point, like I said last time, a point that is on here that isn't on the data table, but we can assume it's on there, is 0, 0. So I'm going to go grab that, make that brown line. Okay. Yeah, something like that. So, what is the formula for the slope of this line? Well, we know that, right? Because slope is equal to rise over run, which is the change in the y-axis over the change in the x-axis. And we know that on the y-axis, we have velocity, and on the x-axis, we have time. And right away, that should ring a bell, right? Because that is equal to average acceleration, or we'll just call it acceleration. Once again, it's instantaneous acceleration if it's over a short period of time, and if it's over a large period of time, it's average acceleration. So the slope is acceleration. M is equal to acceleration on a velocity versus time graph. So what we're seeing here is the slope and area of graphs is meaningful based on what the units or what the quality is that is on those axes. And in this case, the slope means acceleration, whereas in the last case, in a position versus time graph, the slope was velocity. So it depends on what's on our graph, right? And if you ever don't know, if you're like, oh, I can't keep it straight, how do I know? Well, just write the formula for the slope and then look at what it is. When you write it, if it's meaningful, just if you write it down and you're like, oh, it's delta V over delta T, that looks familiar, and you're like, oh, it's that's acceleration, right? And so you have to just think about it, right? Write the slope formula, write it down, and then think about what that says. And if it means something useful, then good. And if it doesn't, then so be it. Because the slope isn't always going to mean something. But in this class, a lot of times it does. All right, number 10 says, using a high-speed train as an example, talk about the train moving in terms of acceleration when the train is gaining speed from stop A. The train hits a constant speed, which it holds for a time interval, it holds for an interval of time. Train slows as it enters stop B. Okay. And then make a graph of velocity versus time. So, all right. Well, I think the first question said, talk about the train moving in terms of acceleration. All right. So the train is gaining speed from stop A. So this would be positive acceleration. which we know is the slope. Then it says the train hits a constant speed, which it holds for an interval of time. So here we could say constant speed would mean zero acceleration. The velocity is not changing over that time period. And so we would expect to see zero slope. And then the train slows as it enters a stop. So we would expect to see negative acceleration. Or a negative slope. Make a graph of velocity versus time showing this movement. So we're saying that there's going to be positive acceleration, right? And then let me go ahead and do that. I'm going to kind of curve this line. And then it's going to be, oh no, that's not good. I'm going to go back and try that again. So I want to curve this line, right? Come on. This thing just doesn't want to cooperate. All right. Okay, something like that. Okay. The only problem I have with that is it kind of looks like it goes up. Okay, that looks better. And then it's going to decelerate. Well, it's a quick stop. Something like that. It's not great. I admit. It's a little rough on this corner here, right there. So maybe I gotta curve that more. Like that. Okay, something like that. You get the idea. And the idea here, and just to be clear, this is positive acceleration. This would be right here where it's flat, or I tried to draw it flat for some period of time. Let's see if I can do that a little bit better. Right? Where that slope is 0, that would be a equals 0. So that would be 0 acceleration. And then right here, where the slope is negative, we have negative acceleration. And then obviously, the train is stopped at A and at B. All right, and that's about it. So hopefully that makes sense. Not the best looking graph, but hey, I tried. All right, by graphing velocity versus time, the area under the graph is equal to something. Well, let's look at that, right? The area is, if you remember back to math class, area of, say, a rectangle or a square was equal to base times height. And if it was a triangle, the area formula became, so this is a rectangle or square. All right, square. Okay, square or rectangle, right? And it was base times height. And the area of a triangle was equal to 1/2 base times height. All right. By graphing velocity versus time, the area under the graph is equal to what? Well, okay. So if the base is time, right? So let me go with the rectangle here. The base is time, and the height is seconds. What is the area? All right, well, there's a couple ways to think of that. One is in terms of this formula. And if we rearrange this, we see that when we multiply both sides by t, right? Let me grab a different color here. If we multiply this side by t and this side by t, that can cancel those, and we're left with delta x equals t times v. All right, and that really, right, is the same as the area. So the area is displacement. What's displacement? That is the change in position. So the area is equal to the change in position. All right. Okay, that's good. Let's see if we can do something else with that, right? What else can we say? Another way to look at it, right? Maybe you want to look at it slightly differently. Another way, it's so hard to pick a color. I'll stick with black. Another way to look at it is, well, what are the units on time? Seconds. Whoops. Seconds. What are the units on velocity? Meters per second. Well, what happens if you multiply seconds by meters per second? You're left with just meters. So this tells you that the area is going to be something like position. But in fact, it's actually change in position is what it is. So the area under a velocity versus time curve is displacement, or delta x. Now notice I said under, right? And that's a key idea. So if we look at this graph right here, this is the area under the curve. So when we take the area under the curve, I always mean the area between the curve and the x-axis. And you might say, well, yeah, that's the area under the curve, right? Well, okay. What I'm trying to say is this. Let's say you had a graph that was velocity versus time. And you don't have to write this down if you don't want to. If you want to, you can, but if you want to just, I don't know, just listen, you can. That's fine too. So I'm going to make this graph. I'm just totally making it up. All right, so this is velocity, this is time. I don't know what this time is. I'm just making stuff up, right? So yeah, that's fine. Okay, so it has some velocity. We'll say this is positive 3. Then right here it drops down to negative 3. And meters per second, right? And maybe this is time 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. I don't know why I'm writing all these down. 8 seconds, 9 seconds, 10 seconds, 11 seconds, 12. You get the idea, right? I just arbitrarily made this up. 16 seconds. All right. And what I'm saying here is when the displacement that you can know what the displacement of the object is, or its change in position, by calculating the area. But remember what we said the area was, right? The area is between the curve, which is the line, and the x-axis. And check it out right here, right? Between the curve and the x-axis. So we would get negative area right there. What the heck is negative area? Negative area, because we would have a negative velocity, right? Times our time. This is the base, right? And this is the height. Well, when we get that negative area, that's telling us that the object is undergoing a negative displacement. right? That's all that's saying. And so up here, when the area is positive, we have a positive displacement, right? This is positive delta x. And yeah, and that's about it. What does positive mean? It means a change in position maybe to the right. And what does negative mean? A change in position maybe to the left. And so hopefully that's making sense. So not only is the slope meaningful, but the area is meaningful. All right, let's go back and take a look up at a question, and let's see what we can get from this. So describe the motion in the graph in terms of acceleration, positive, negative, or zero. Okay, so let me get a color here. All right, so, oh, and then they tell us on the side what's going on. So from 0 to 2, let's see. So from 0 to 2, right here, we have zero slope, right? And so that is going to be zero acceleration. So I'm filling it in right over here to the right. Hopefully you can see that. Okay. So then from, say 2 to 4, right? I don't know if you can see that. That is a positive slope. So I have a positive acceleration. Slopes that are up and to the right are positive, down and to the right are negative. You get the idea. All right, so this is going to be negative acceleration right here from 2 to 4 seconds. And then from 4 to 5 seconds, once again, we have zero slope because it flattens out right there. Let's see if I can grab that red back. So right there, from 4 to 5, once again, we have zero slope and zero acceleration because acceleration is the slope on a velocity versus time curve. And then from 5 to 7, we have negative slope or acceleration. So, all right. I'll go ahead and color that blue. All right, so you get the idea. Okay. What is the object's velocity? All right, so pretty much what this amounts to, when we get a velocity versus time curve, we have three ways of having questions. We either have a right there question, which we just read the graph, which these are, or we have a slope question because we want to know acceleration, or we have an area question because we want to know displacement. All right, so this one's actually just a right there question. What is the object's velocity at 1 second? Well, at 1 second, we just follow this up, right? If you can see where I'm drawing right here, I follow that 1 second up to the curve, and we see, I'm going to erase that because that's kind of, whoa. All right, I erased a lot there. That's okay. I'm going to erase all that. It doesn't need to be there now. At 1 second, let me grab another color. This bright green, right? It's going to be equal to 2. So that's where the line is, right? So let's go ahead and write that in. So it's very simple. Don't forget your units. At 3 seconds, let's grab a different color. Let's go, yeah, what the heck? Let's go pink. 3 seconds, right? It's right here, which is at 3 meters per second. 5 seconds, you can see where this is going. 5 seconds, it's going to be at 4 meters per second. And 7 seconds, it's going to be all the way down there at the x-axis, which is 0. I'll circle that right there. All right, so you can kind of see where that's going right there. All right, then part C, it says, what is the object's acceleration at 1 second, 3 seconds, and 6 seconds? Well, at 1 second, we can see, right, that the slope of this line is going to be 0, right? At 3 seconds, we have to calculate the slope of this segment. And at 6 seconds, we have to calculate the slope of this segment right here. All right, so to do this, we're going to use the slope formula 3 times, and obviously the first one's going to be 0, right? But I'm going to go ahead and calculate it. So let me see if I can get another piece of paper here. Somewhere, somehow. Okay. So let's go ahead and give this a shot. So the trick here is this. When you find the slope of a line, you get to take any 2 points off that line and calculate slope. Now, if I look at just the blue segment here, it looks like there's only 3 points, but actually there's an infinite number of points. But I'm going to grab one of the 2 of the 3 because it makes it easy. So on the blue segment, I'm going to take this point and this point right here. All right? And then I'm going to come down here and calculate slope. So slope is the acceleration, which is equal to delta V over delta T, which is equal to VF minus VI over TF minus TI. Now, if I look up here, let's do the times first, because I think it's easier to do that. We can see that we have 2 times. We have 2 seconds for the first, right, for the first dot, and then 0 seconds for the second dot. So I'm just going to go ahead and use 2 seconds as my final. 2 seconds has to happen after 0 seconds, so it has to be final. Another way you know that is on the bottom, time will never be negative. There's no such thing as negative time. So it's always going to be a positive bottom of your fraction. The top might be negative, but the bottom always has to be positive. All right, at 2 seconds, what's the velocity? Well, VF is 2. At 0 seconds, what's the velocity? Well, at 0 seconds, VI is 2. So we subtract 2 minus 2, which is just equal to 0, divided by 2 seconds. And it's always okay to have a 0 on top of your fraction. If you have a 0 on bottom of your fraction, you're in trouble, because then it's undefined. So 0 divided by 2 is just 0 meters per second squared. So there is the acceleration at 1 second. So I'll just make a little note there, at 1 second. Okay, let's go ahead and try that again. A equals VF minus VI. I always like writing these out multiple times because it's good practice for memorizing your formulas. All right, so now we're going to look at the orange segment. Let me see if I can erase some of this. It's getting kind of crazy. All right, maybe if your graph's getting too crazy, that's fine, and whatever. Just try the best you can. So I think we said orange. Okay, so now we want to find the slope at 3 seconds. Now, one of the things you might be noticing is when I want to find the slope at 3 seconds, you think I would use this point right here where the star is. I'm not going to. I don't have to use that point. I just have to use any 2 points on the orange segment. So I'm going to use this one and this one just to be difficult. I could use 3 seconds, but I don't want to. All right, so now I'm going to come down here and do that. All right, so my times there, I think if I look back up, are 4 seconds and 2 seconds. So I'm going to go ahead and write those times in. 4 seconds minus 2 seconds. At 4 seconds, our velocity is what? Well, it looks like 4. All right, everybody agree? Yeah. And at 2 seconds, we're at 2. Okay, so, all right, pretty straightforward. So final velocity is 4 meters per second at 4 seconds. Initial velocity is 2 meters per second at 2 seconds. So we end up getting 2 meters per second divided by 2 seconds, which is equal to 1 meter per second, right? Which is also equal to, and that's an A, is equal to 1 meter per second squared. All right, and so we have the acceleration this is at 3 seconds. All right, so far so good. Let's get the next one, right? Which is at what was it? I think it was at 6 seconds. So I forgot what color I used. So I'm just gonna grab a color, not orange. Let's go purple. All right. And that is the segment we're interested in now. So once again, I'm going to take any 2 points. Don't have to use the one at 6. So I'm going to use the 2 end points. So 7 seconds and 5 seconds. All right, so coming down here then, acceleration is equal to VF minus VI over TF minus TI. Final velocity is, or no, I'm going to do the times first. So 7 seconds minus 5 seconds. Now, what was the velocity at 7 seconds? I think it was all the way at 0. Yeah, so at 7 seconds, it's down here at 0. And at 5 seconds, it's up there at 4. Okay. So I'm saying 0 meters per second minus 4 meters per second. Oh, that's going to be a negative number, right? So we get negative 4 meters per second over 2 seconds, which makes sense because it's a negative slope. So we would expect to see a negative number here. Negative 4 divided by 2 is negative 2 meters per second, or negative 2 meters per second squared. And this is going to be equal to the acceleration. And this is at 6 seconds. And this is how we calculate instantaneous acceleration, right? Because we're getting the acceleration at one time period. And this works pretty well because we have these nice slopes. But you can see how it's different than an average acceleration where maybe we used the initial time and the final time, right? And we got all points in between. Here, we were breaking these segments, or this graph, down into different color segments where the slope was constant to find the slope or the acceleration. And so this is an instantaneous acceleration we're calculating here in a way, because we're getting the acceleration at certain times. We didn't have to do a tangent line because it's not a curved graph. These are nice graphs for us, except for these. There is one thing I just want to mention because it's not asked of us. The only problem, what the heck? I thought I just erased all that. Okay. The only problem is at, you notice we never asked for the slope at say 5 seconds. And why is that? Well, at 5 seconds, the graph is doing something weird. It's called a corner or a cusp, right? And at a cusp, we don't know what the corner belongs to. We don't know what that point belongs to. Does that point belong to this purple section, or does that point belong to this 0 section up here? Let me put that 0 section in maybe a different color. Maybe, I don't know, green. Okay, so which slope is it part of? Is it part of the 0 slope or the negative slope? And we don't know. So therefore, if that question was asked, you would say that the acceleration is undefined there. So you have to have real objects that are moving don't have these corners or cusps in their motion. They don't have this this jagged motion, right? Their motion is curved, and so I just want to point that out because yeah, it would be undefined if we asked for that slope there because we don't know which slope it belongs to. All right, good. Part D, the formula for the area of a rectangle, area of a triangle. We already did that. It's up above. Part E, how far from the starting point is the object at 2 seconds and 7 seconds. Use the formulas above. All right, so we just did this a second ago. And we said that the area of this graph is determined by the area under the graph, right? So for 2 seconds, we only care about this area right here. And you can see that the shape of that's going to be a square, right? So we're going to go ahead and calculate the area. Area is going to equal base times height. I don't know why that's there. Okay. And that's equal to, the base is going to be 2 seconds. The height is going to equal 2 meters per second. And you can see seconds will cancel away. And we're left with 4 meters. So the change in position for this section is positive 4 meters right there. And that's our answer for 2 seconds. Now, it's a little trickier in the next part where they ask about 7 seconds. So at 7 seconds, that's the entire graph, right? So now, the reason this is trickier is because I don't know how to take the area of that shape. I don't know what that shape is. So what we do to make this easier is we break this up into shapes that we know. So I'm going to leave the positive 4 meters because that's the area of that square. I have to get the area of this right here, which is, let me see if I can, this right here, right? I have to get this area now. And I don't know that shape. So I'm going to break it up into shapes I do know. For instance, I know that this right here is another one of those squares that I just found the area of. So I know the area of this square right here is positive 4 meters. And you can do that if you want and show your work for that, but it's going to be the same calculation we had before. The base is 2 seconds and the height is 2 meters per second. Why is the base 2 seconds? Because it's 4 minus 2, right? And so that's the area of that. This triangle up here, we'll get the area of that, but it's going to be 2, but I'll find the area here in a second. How did I know it's going to be 2? Well, the triangle formula, right? And this is going to equal, the area is going to equal 1/2 base times height. Well, all right, what's the base there? Well, the base here is right here, and the base has to be 2 seconds. What's the height? The height is from 4 to 2, right? So it's going to be 2 meters per second. All right, so then I take 2 times 2, which is 4. I can cancel off my seconds. And we get 1/2 of 4 meters, which is 2 meters. So the area of this triangle right there is positive 2 meters. Can I write that in there? Maybe. Okay, positive 2. That's kind of hard to see. I wonder if I can erase. Ugh. Of course, I started erasing everything. That's just the way it goes. All right, something like that. So that triangle is positive 2 meters. All right. And we got 2 more shapes left. This larger triangle, and we've got this rectangle here. So the rectangle right here is going to have an area equal to base times height. Base is 1 second because it's 5 minus 4. And the height is going to equal 4 meters per second. If I'm going too fast, slow this down and prove that that's the case. So the area here is equal to 4 meters, positive 4 meters for that. And then finally, this triangle right here, area is equal to 1/2 base times height. And here the base is 2 seconds. And the height is 4 meters per second. So 1/2 of 8 is going to equal 4. And that's positive 4 meters. So my point is, let me go ahead and write that in. Oh, that's kind of hard to read. All right, so what we have here then for this area, right? We have, let's count it out here. So we have a positive 4. Let's see if can I show this somehow? Maybe. Let's see. All right, I'm just go back to the really bright blue. So we have a positive 4 there, positive 4 there, positive 4 there, and a positive 4 there. So that's going to be 4 plus 4 plus 4 plus 4 is 16, and then a positive 2 right there. 16 and 2 is 18. So the area here at 7 seconds is equal to 4 meters plus 4 meters plus 4 meters plus 4 meters plus 2 meters, which is all equal to 18 meters. All right, hopefully that's making sense. And let me know if you have any questions. Hopefully my math is all good. I don't have you guys, when I'm lecturing this way, I don't have you guys to point out any obvious math errors. So if I made any obvious math errors, just let me know in class. I'm sure somebody will. Somebody always usually tells me, and I appreciate that. So, all right. Anyways, have a good night, or good day. Yeah, good night. And I will see you in class next time. All right, take care.